Some of the most exciting places to search for life in the solar system are the moons of the gas giants, like Europa and Enceladus. These are frozen worlds, their crusts composed of thick plates of ice, pushing and breaking apart like tectonic plates on Earth. Beneath this crust of icy sheeting, on each moon there's a liquid water ocean. Evidence suggests these liquid water oceans are pretty salty, meaning there's minerals and nutrients mixed in. There's some contact with the liquid water ocean and some sort of mineral bedrock, perhaps at the core of the moon. Differences in temperature caused by tidal heating, tidal warping, this might induce currents that can create some kind of order and consistency to the aquatic ecosystem, some stable patterns flowing through the moon's ecology. Unfortunately, the potential for life in these environments is still unknown, although they're widely hypothesized to be some of the most potentially fertile areas in the solar system for life besides Earth. The evidence is tantalizing, but more research always needs to be done. Now today, I want to tell you about some of that research, which has provided some insight into the surface conditions of Europa. So, some background information before we get started. The surface of Europa is a rippled, fractured landscape, where sheets of ice buckle and crack as they jostle against one another. And all this roughness and fracturing creates fissures and cavities in the ice, and liquid water from beneath the ice can come surging up. There's a pretty strong pressure differential here too. This water can surge up through all of the ice caverns and crevices to blast out or leak out or bubble out onto the surface. It would probably be bubbling out. In places where it wasn't a geyser due to the pressure, the water would probably be bubbling out because the low pressure atmosphere would mean that any liquid water that does make it to the surface would rapidly boil away into vapor. That is, if it didn't freeze onto the ice itself. Now, if there is life in the oceans of Europa, then it's possible that some microbes, or at least some biological chemicals, could be detected in some of this water surging to the surface. Now this is feasible, but there's a problem. Due to the lack of an atmosphere, the surface of Europa is sterilized with radiation. Any microbes would be killed pretty quickly, and any biological molecules might be quickly broken down. This means that any evidence of alien life in the bubbling streams of water leaking to the surface may be destroyed before we ever get a chance to analyze it. But there is good news. Previous research has found that just 8 inches of ice, or about 20 centimeters of ice, is probably more than enough to shield these potential biomolecules from the radiation. And now this is where today's news comes in, as it's yet another development in our understanding of Europa. Now, this particular study was focused specifically on the impact gardening of Europa, or in other words, the rate of small impact events that gradually churn up the surface layer of the moon. On a planet with an atmosphere, all of these smaller impactors, these micrometeorites and whatnot, they would all be burned up in the atmosphere. But Europa, as well as many other moons in the solar system, don't have an atmosphere. They don't have this little protective, puffy layer to shield the surface from these micrometeorites. And so on Europa, we see that the surface is pretty regularly churned up by all of these impactors, by all these little tiny impact events that are constantly happening. That was the main gist of the study here. The biological component of their study is actually largely tangential to what they were looking at, in the sense that their research wasn't focused on any specific biological phenomenon, but it does inform our speculation on potential alien life on Europa. So the researchers found that impact gardening occurs all over the European surface, leading to a churning effect of the upper 12 inches or so, or about 30 centimeters, of the surface ice. Now, in simpler terms, the lack of an atmosphere on Europa, it can't burn up these little asteroids and stuff, so they all pepper the surface pretty much all the time. These impactors disrupt the upper foot or so of ice, meaning that any liquid water there can't rely on the ice for long-term protection. Biomolecules will be destroyed if the protective ice layer is punctured and ablated by a multitude of small asteroid impacts. Due to this phenomenon, this garden impacting, The researchers suggest that the best place to look for life on Europa would be where the effects of radiation and impact gardening are minimal. This includes inside the basins of fresh impact craters and in the mid to high latitude areas. They also suggest that if we are to search the surface for signs of life in these water seeps, we may want to design a drone or a robot or something that can dig at least a foot into the ice before sampling for water. This stuff might seem a little dry and technical, but it's really important. If we're going to successfully find life on Europa, assuming it's there in the first place, we'll need to really understand the geophysics and the ecology of this moon, of its icy surface, so that we can optimize our search strategies. What are we looking for? Where are we looking? What parameters should we design into our Europa probes? All of these questions in our search for alien life will be informed by studies like this.